Let's jump right into this explainer. We're exploring a seriously fascinating paradox in AI research today. You'd probably assume that giving a computational model a perfect, infinite memory would make it vastly superior, right? Like letting an autonomous agent flawlessly reference every single past interaction. But the data from extended conversational benchmarks actually shows the exact opposite. Forcing an autonomous agent to remember absolutely everything without any regulation completely destroys its ability to perform over time. Let's zero in on a very specific number, an 85.27% catastrophic performance drop. That is massive. On the LOCO benchmark, which is designed to test long-term memory persistence across temporal stages, the OpenShot 3.5 model saw its memory score literally plummet from 0.455 down to a mere 0.05 across extended interactions. And this massive degradation is the direct result of just leaving memory accumulation running without any explicit constraints during long horizon tasks. This really illustrates the ultimate stakes here in AI design, short-term computational brilliance versus long-term degradation. Because if an autonomous system can't maintain contextual coherence without degrading over extended dialogue sessions, well, true autonomy is simply impossible. It really doesn't matter if a model scores perfectly in the first 5 minutes if retrieval noise makes it completely lose the plot an hour later.
So today we're looking at a paper that proposes a fix for exactly this problem. One thing up front though, this is a theoretical framework paper. Every number I'm about to show you comes from other researchers' published benchmarks. The authors haven't run their own experiment yet. They're arguing mathematically that their approach should beat those numbers. Keep that distinction in mind as we go.
Section 1. The AI memory paradox. So the root of this paradox is a phenomenon known as context bloat. This happens when you have an uncontrolled accumulation of memory, which directly increases retrieval noise and computational overhead. Think of it like a wildly messy digital desktop. If you keep every single document, image, and file you've ever opened sitting right there on your screen, finding the exact one you need is going to take significantly longer. And worse, you drastically increase the risk of grabbing outdated or incorrect data. In an AI agent, aggressive random deletion reduces contextual fidelity, but unmanaged growth skews the memory relevance distribution entirely. We can see this perfectly in the baseline data. On the MultiWAS 2.4 benchmark, which evaluates task-oriented multi-domain dialogue, an unconstrained model managed a 78.2% accuracy, but it simultaneously suffered a dangerous 6.8% false memory rate. That contamination happens precisely because uncontrolled accumulation inevitably retrieves contradictions from outdated information.
We can see the same pattern in a separate benchmark. On the MultiWAS 2.4 benchmark, which evaluates task-oriented multi-domain dialogue, a persistent retention model, one that keeps everything with no forgetting policy, managed 78.2% accuracy, but suffered a dangerous 6.8% false memory rate. That contamination happens precisely because uncontrolled accumulation inevitably retrieves contradictions from outdated information.
Section 2. Adaptive budgeted forgetting. So how do we fix this? Instead of a massive, unorganized data dump,
the paper proposes a structured, multi-layer memory state.
The architecture divides data into working memory for immediate tasks, episodic memory for session-level summaries, and semantic memory for long-term knowledge like entity-event relationships. But here's the crucial part. These layers are actively regulated by a budget-constrained module that prioritizes what stays and what gets overwritten through an adaptive control loop. Section 3. Scoring memory relevance. To understand exactly how the system decides what to delete, we have to look at how it scores memory relevance. The framework treats memory retention as a constrained optimization task, relying on 3 specific pillars to calculate an importance score for every piece of stored data. First is recency, which uses an exponential temporal decay factor so that stale info smoothly attenuates over time. Second is frequency, accounting for reinforcement through repeated usage. And third is semantic alignment, which measures how well the stored memory matches the active mathematical query.
Combine these 3 weighted signals, and you get a unified relevance score across heterogeneous memory components.
This brings us to the core mathematical engine of the paper, bounded optimization. Rather than just blindly deleting the oldest data based on chronological order alone, this system mathematically targets low-importance entries to stay strictly within a predefined memory budget. By penalizing excessive memory usage through its loss objective, this targeted pruning directly cuts down that retrieval noise we talked about earlier. It preserves the model's reasoning capabilities while maintaining a highly efficient footprint. Section 4.
Comparing against the literature. Here's where I have to slow down, because this is the part that gets misrepresented most often. The paper does not run its own experiment against these benchmarks.
What it does is line up its proposed method's theoretical constraints against results other papers already published, and argue that meeting those constraints should beat them. On Locomo, a different team's hierarchical memory architecture pushed overall F1 from a baseline to 0.643 under a full dynamic ablation setting. That's someone else's result, not this paper's. Smaller baseline models in that same study scored as low as because of their sensitivity to long horizon memory growth. What this paper's table actually claims is that its own approach should exceed 0.643, reduce false memory rate below the multi-WAS figures, and do it without increasing context usage. Should, not measured to. There's no dataset section here showing the framework actually running. Section 5, the future of agents. So what should we actually take away from a framework that hasn't been empirically tested yet? As a speculative hypothesis, if this mathematical approach does get implemented and holds up under real testing, it could pave the way for more resource-efficient, persistent AI assistance. We're looking at a potential future where models maintain coherence over extended timeframes, running locally on your own devices without needing massive context windows that drive cloud computing costs and latency through the roof. But that's a bet on a proposal, not a confirmed result. To wrap up, here's the actual takeaway. True systemic intelligence probably isn't just defined by everything a model can theoretically store, but by which data points it deliberately chooses to forget. If that's right, what does it mean for the massive context windows tech companies are currently racing to build, and are we sure anyone's actually tested the alternative yet? Definitely something worth sitting with. Thanks for joining me on this deep dive into adaptive budgeted forgetting.